Hello everyone, this is lecture 7 of Advanced Drilling Engineering, PTRE 451545. I did upload lecture 6 last Thursday, but I forgot to send the announcement on Blackboard, but it has been there. Well, it should be the recording. We have been discussing, we stopped last Thursday, right where we were talking about cementing. And I think we are about 15 slides away from the first homework. So it should be coming soon. Probably I will try to ideally upload it before this weekend, if it makes sense, if we have made it there. But the first homework is fairly easy. It's fairly easy, but it's the most easy but important. Like those equations that you are using in the first homework that you learn how to use, hydrostatic calculations, it's gonna be basically the bread and butter from moving on. It's a little bit of a hierarchical theme, I guess, this class. So it's like if you miss the beginning, you're not going to be able to get the other stuff later on, because what you learn, you use them later, you apply them later. So we have been discussing cementing, and we said that a normal cementing job, what you expect to be done when you're on the oil field, you run casing, you pump cement, you get cement, pump cement downhole from the inside the casing, and you get it through the annulus, and you let it basically settle. That is primary cementing. Secondary cementing is mostly for remedial purposes, like you are doing it to fix cementing jobs that are not good so far, and stuff like this. Let me move the bar here. I cannot see anything. There you go. So cementing, when we say primary cementing, that's basically the normal cementing operation. If you really do it right, and sometimes it's not dependent on you, you don't need a secondary one, but many times you do. There is a series of procedure and tools that are needed during a cementing job. And many times you can deviate from this plan. You can go, you can maybe not use this particular tool. You may want to do the job a little bit differently, and sometimes it will work. It might save you some money as well. Nevertheless, every step that you take away from the proper procedure, it makes it easy for you to fail. And if you fail with your cement job, it can be very, very detrimental. It can be very, very detrimental. It can be as bad as you have to abandon the well. It can be, or cost you a great deal of money. So for the casing and cement tables, we did mention last time the Halliburton Red Book, and I brought my own from the office, pass around, with all the data for the available tubulars and cements. It's available in app nowadays, and we used to use it for our homeworks back in my time when we did undergrad drilling. So the centralization of the casing is important, because you want to keep it in place. If you have the casing touching the side of the well, then cement is going to be hard to pass through that point. So you really want to keep the casing centered as much as you can. And this is not easy, as you can understand. It's very, very easy to have the casing touch the side of the borehole, and then it's very hard to pass cement through that space. We use centralizers for that, and There are different types of centralizers, and we're going to talk about those. But yeah, when you hear the word remedial, it's like to fix something, and that's about the secondary cement operation that I mentioned later. So yeah, secondary cement means that you already have cement in place, and then you go again. So we passed through this slide. We went through it last time, actually. So here is some of the necessary tools that you need, and we're going to discuss those. You need a guide shoe or the casing shoe. We're going to talk about those. At the bottom, this is used to help the cement go from inside the casing to the outside. And the annulus, it's shaped in a certain hydrodynamical shape that allows the cement to flow like this. Then we have centralizers that I mentioned earlier. And centralizers, there are several kinds of centralizers. This is a bowspring centralizer, and you can put as many as you want at different places in the casing. This is to keep the casing in the middle. A float collar, which basically allows flow only in one direction. It's like a flapper valve. It has a flapper valve and basically only allows cement to flow in one direction, forwards and not backwards. And these days, you can find casing shoe with a float collar, basically the same thing. So this and this can be combined as well. Some companies have tried that. And there is such tools. Sometimes you should use it, sometimes you should not. Another, above this, is the bottom plug. We are going to talk about it. It's normally colored red or orange. It is important. And then the top plug is color black or yellow. Okay, and these are important, the sequence in which they go through the well. If you get a very bad employee who puts the top plug in first and then the bottom plug, you basically lost the well. We'll explain why. When you pump cement, you are driving it with mud, okay? You are pushing the cement slurry with mud. But sometimes the mud, most of the time, should not mix with cement. It gives you some, it's gonna create some reactions that you don't want. It's gonna basically contaminate your mud. Your mud is gonna precipitate stuff that you don't want it to do. It's gonna cause damage. So there is some spacer fluid, which is basically a brine or just fresh water in between them. We call it displacement fluid or spacer. Oh, sorry, spacer. You don't see it in this picture. Displacement fluid is generally mud. And this is how you dry it. Now let's see what we have here. Oh, and at the top, you see the cementing head. The company that is doing your cement job, basically Halliburton or somebody, is going to bring their own cementing head and attach it on the top of the well, and they will pump the cement from there. These rubber plugs that we mentioned are very important. Basically are the beginning and the end of the cement slurry. And they are supposed to basically provide a separation between the slurry and everything behind it. Of course, separation is not possible. That's why sometimes we need the spacer fluid that I mentioned earlier to create a gap between the displacement fluid and the slurry still, because even if you have the plug, you still have contact. The cement slurry is driven with drilling mud separated by spacers, which are chemical washers. A cement head is fitted to the top joint of the casing string to facilitate cement injection and is connected to the circulation line by a manifold. Now, two types of cementing plugs are typically used in cementing operation. The bottom plug, which is red or orange, is launched ahead of the cement slurry to minimize contamination by fluids inside the casing prior to cementing. Basically, it has mud below it and cement above it. This is the bottom plug. It goes on first, okay? Now, the bottom plug is very different than the top plug in a sense that it has this little membrane here. It's a diaphragm. It's very easy to rupture it, break it. You just apply pressure above a certain level and you break that diaphragm. And this lets you pump through it, okay? You hit it, if it touches somewhere and it stops, it will be the float collar and it stops. And then you keep pumping, it raises the pressure above it. You keep pumping, you apply more and more pressure, and then this ruptures, and then cement can flow through. It will rupture intentionally, basically. This is the bottom plug. The top plug, I think I have an animation. Is it? No? No animation? Oh. Okay. I thought it was an animation. Okay. There you go. Is black or yellow sometimes. It's basically a solid body. It's very similar to the bottom plug, but it's missing something. It's missing this diaphragm. And it basically has a very, very strong, top section. You can pump as much as you want through the top. You're not going to break anything. Okay, so between the two slurries, the two plugs, so here basically, I mean, now they are touching each other, but between them is the cement slurry. Once you break the diaphragm of the red plug, and you are gonna push the slurry underneath, like through the bottom plug, and it's gonna go through the annulus of the well, etc., etc. And then the top plug will move down and touch that. So this is what you want.
Sorry.
Yeah.
The spacer you mentioned, what position does the spacer occupy between these two plugs?
The spacer is above this. Above this, yeah. The spacer is here, and the displacement fluid is here. You may not want spacer either. I mean, basically the cement is between those two plugs. Now you broke the red plug, the diaphragm, and you push the spacer, the cement slurry down until the top plug touch the bottom plug. Okay, so now what you have is basically the casing shoe, the float collar, the bottom plug, and the top plug. You're going to have to drill through them, right? You're going to have to drill through them. These ones, they are rubber. You can drill through them fast. You will drill through them fast. And then you're going to drill through the casing, the float collar, and the casing shoe. It's not going to be that easy, but it's going to take like 3 hours or something to drill through them, maybe more, maybe less. But this is when you did it right. Say that the guy that was responsible to put the plugs in made a mistake, and he put the top plug first, the black one, and then the red. What do you think will happen?
The what?
Somebody messed up the plugs.
I'd rather put the
Red one on top of the black.
black one.
Yeah, then what will happen?
The slurry will not
The
flow.
slurry will not flow, and then there's not going to be break.
Yeah.
You'll not break because
Where is
that
the
one-
slurry gonna stay?
the slurry is going to be on the top.
In between.
In between, which is in the middle of the casing,
Yeah.
and then it's gonna solidify.
Yeah, okay.
So unless
And
you
then what do you have to do?
drill it.
You have to drill it.
Yeah.
You're not gonna drill it. You're gonna lose your job.
You go out to apply for another
But if
emergency.
you way forward to resolve that, if
You
you
got
make
another
somebody make that mistake, if somebody make that mistake, what is the way forward to get it out?
You cannot get it out. How are you gonna get it out?
No, you are saying that the red, that's where the diaphragm is very fragile.
Yeah.
That if you put a pressure above it,
It breaks.
it breaks. And that is where the cement slurry pass through to the down
Yeah.
and then now inside
Yeah.
the casing,
Yeah.
right? The between the casing. So now when you turn this,
Yeah.
right, is this, so this one will be there and then this one will be rather break and this one cannot break.
Yeah.
So the slurry cannot enter here and come. It's going to now be on top,
Yeah.
solidify over there,
Yeah.
and then be inside
Yeah.
the wellboard. So the only way is like you have done a plug and abandoned like that. So probably
Yeah. It's basically you're gonna lose the well. You rather go elsewhere and start drilling another.
really. So you
Yeah.
can't do anything.
So you can't drill through.
You can't really.
You can drill through. It's gonna take. It's not worth it.
Wow.
Well, it's not worth it.
No, most of the time it's not worth it. I mean,
Okay. If it's not worth it, we
well, it depends also how tall the column is. If it wasn't a very tall column, you
Uh-huh.
might. But I mean, it's a big mistake, right?
okay, but in the normal way, like this,
Yeah.
if we install them in the right way, where the red one, the red block is down here, the black is up there,
Yeah.
and this, that is where we apply pressure, the diaphragm break. Cement slurry pass through,
Yeah.
come inside the
Yeah.
annular casing, annular, and then start cementing. Then this one now come down as a casing shoots
Yeah.
down,
Yeah.
down
yeah.
there, right? So
It comes down, it touches the float collar before it breaks.
yes, so and then this one also now press
Yeah.
and then come down. So how do, you were saying that we normally not drill this as a debris out, this one
Yeah,
because
these are very easy to drill through.
so how is the drilling bed is going to pass through this one and through?
Yeah,
and then
yeah, it's
drill?
very easy. I wish I had the rubber plugs here to show you. The Colorado School of Mines drilling professor, the old one, had in his office. They're very easy to drill through.
Wow.
They are made of rubber. You are gonna drill through it faster than the float collar and the casing shoe. That's for sure. It's not a problem. They are made like this.
So it's like this, right?
Yeah.
This is our top one,
Yeah.
and this is the bottom one that is fragile that
Yeah. Yeah.
we
Yeah.
can easily drill through. So now, when if this one break, the diaphragm break, this one now settle down like this to the casing, and this one will sit on it like this.
No, it settles down. The bottom one settles before it breaks because you need to apply pressure.
Yes.
If you apply pressure, it's moving until it touches the float collar.
Mhm.
Actually, it's moving until it touches the float collar, and then you apply pressure, and then it breaks, basically. You see, this one is gonna touch the float collar,
Mhm.
and then it's not gonna be able to move anymore.
Mhm.
It's gonna break,
Mhm.
and then you get the cement slurry going like this, which is what you want,
Mhm.
right? And then until this one touches this, and then you have to drill through this, and this.
You drill through the first one too,
Yeah, the top one.
the top one.
Yeah.
That is the same thing that we say if we made a mistake, we can also drill that one.
No, you have to drill also in the whole cement column. It won't be a problem drilling through the plug.
Okay.
It will be, basically, you will be here, you will have this cement,
Uh-huh.
and then this, on top, sorry, you have this, a
Down.
bunch of cement, and then this.
This.
So it's the
Lock.
cement the problem that you have to drill through.
Okay.
You might have the whole well filled inside with cement, so you need to go again with a smaller bit
There.
and drill through. might be easy, it might not be that bad, but it's pretty bad. They may not abandon the well, but you will still probably lose your job.
Yeah, you lose your
Yeah.
job for that big mistake.
Yeah. Which is
Right.
why they are saying,
What if the first error? The first error committed by the engineer. The first mistake committed by
Well,
the
my drilling professor used to say that if you work for the operator, go there and make sure you see the plugs going in the proper way, because he's an employee of a service company that you hire, that you contracted. It's your well. So
Yeah.
go there and make sure that they put the plugs the proper way and everything.
Yeah.
Um,
But if you are an engineer, say a new engineer, how do you avoid this kind of problem?
well, if you are a new guy, you are shadowing somebody that
You are under somebody's supervision. That's why you're learning under
you are
somebody.
like the junior guy, you are shadowing somebody, or you are generally the cement people is like one main guy that they send, and he's like very experienced, and he can take care of the job on his own, or they send him with somebody junior that is learning and can basically do it properly. And then eventually the junior guy is doing the job and the big guy is watching him. And then when they are comfortable, they can send him out on his own. Yeah, it's unlikely that, like all the cement people that I met, they were pretty like, pretty covered. It wouldn't be that mistake. It wouldn't be that mistake. I mean, probably
They
also.
have different colors, so I mean, you shouldn't.
It's not just the color, you can see it when you take the plug. I wish I had to show you guys. It's very visible that is different, because look at that. I mean, there's a big difference between this and this, and I'm pretty sure the companies, when they sell them to you, they will make sure that you know which one is which. I mean, yeah, it's not like they want you to buy. Yeah, they want you to buy this again, right?
Yeah, the centralizer
Yeah,
that we use to position the casing in
Yeah,
the
yeah.
center of the
Yeah.
this thing to position the casing very well whilst doing the casing. How do you remove the centralizer?
you
Is it
don't.
that is the cement slurry, won't it also come in and then be able to?
You don't, because the centralizer is on the annulus. The centralizer is here. You're gonna have cement all the way here that solidifies, and here. So you don't care about the centralizer. The centralizer is there to make sure that cement flows through it. But the centralizer, this one, this is what you have. You want to have cement, so solid cement that will stay there. This one.
Yeah, but won't the cement also cement the centralizer that's be able to hold the casing? at the
Yeah, that's
center?
fine. That's fine.
So you leave it inside
Yeah, yeah.
the central, okay.
Yeah,
thought after that
it'll
you
stay
will-
inside.
I thought you remove them after the,
No.
okay.
Centralizer is very, very cheap, very. It's used to stay there. Is some of the centralizers you can move them with your hands even. But yeah, this is where you want the cement to go, and this is your goal. The problem is when you don't want the cement to stay here and solidify there, because then you have to go and drill it. Now, if you make the mistake and this whole thing is filled with cement, basically you didn't drill. It's almost like you have to drill a new well. It's almost as strong as rock. So it might be, yeah, I mean, you might as well move and drill another well or sidetrack or, yeah, I mean, this is why you don't want that to happen. Any questions?
So the plugs, do they have specific diameter?
Yeah.
Just a specific diameter, because if you have different section of the hole,
Yeah. You're gonna use different size, but still you're gonna have a bottom plug and a top plug, and you have to put them a certain way. Yeah, it's not yeah, it's very, they are rubber plugs. You almost can squeeze them. It's not they are light. They are light and very easy to drill through them. Very easy to drill through them. Might take like minutes to drill through them. So this is the float on the landing collar. Now I have it upside down here because that's where was the picture I got it. So imagine the way it works. Imagine, and I know it's weird, like the mud cement flowing through like this, okay? Because it's upside down. Okay, when you pump cement through, you have this little, here is the sealed ball, which is like a little seating. And if you apply more and more pressure, this spring gets compressed. It moves down and it creates a pathway for the fluid, which is cement, to move like this through the basket down and basically down hole. Now, if you notice, if you do your job right, basically, you're gonna have, as we said earlier, let me use the right colors. We said the bottom plug will touch here, right? And then all the cement will flow through the float collar, and the top plug will sit on top of that here. So you have, right? You understand? It's upside down. Okay. But if you see here, everything except the pipe body is metallic. Okay. The basket is also metallic, but they can make it with other material too, synthetic materials. A lot of part of this float collar is made intentionally with cement or other synthetic materials that are easier to break. They are drillable. So some of them are also degradable with temperature. So when the temperature goes up, it's made this way to assist you breaking, to drill through it after you finish your job. So this is why we have the main purpose of the float collar is just one thing, is it will allow cement to flow through like this, as we said earlier, but like this, but never like this. Because if you try to go the wrong way, this spring will expand in tension and it's gonna seal, the sealed ball will seal this little spacing, and then you are not gonna be able to go one. So it only goes one way. It doesn't go the other way, right? And there are several designs. This is only one design. I'm just saying that this is how important it is not to leave cement inside the casing. You want only cement on the annulus. That's why you take all these precautions. You may want to use 2 float collars. Okay, then you have a little bit of a short section of cement to drill after the cement job between the 2 float collars. That's generally fine. It's not gonna be a tall cement column, but do whatever you want as long as you don't leave any cement inside the middle of the well. Other designs like this, with a seal ball, with this little pointy triangle, they all work the same way, in all honesty. They just allow cement to flow in one direction and not the other. They want cement to flow through them down and not upwards. Any questions on the float collar? Okay. Now the casing shoe, it's a rounded shape profile component. This one, I flipped it correctly. It's basically the shape that allows cement to flow from inside the casing outside, outside. This is what the casing shoe or guide shoe allows. It was invented in 1907 by Carl Baker, who eventually became Baker Atlas, then now it's Baker Hughes. Right, and it allows the cement to flow through properly. Sometimes there is a float valve inside. Okay, which is very similar to the float collar. Sometimes you have now, these days, you have a casing shoe with float collar combined. And by the way, the casing shoe is much longer than what you see here. It's like very long. It looks like a joint. And it comes to the rig on a separate track, like with just that one. Because it's sold separately, the casing shoe. It doesn't come with the casing, strings or the drill pipe or this. It comes with a track on its own most of the time, and this is the casing shoe. And yeah, I mean, the valve is to prevent U-tubing. U-tubing is basically cement going the other way. Cement flowing back like this. You don't want that to happen. So you have this check valve, just like the float collar, okay? Everything is very designed such that they do not allow flow the other way. Here you have this little black ball, which basically, if you apply pressure from one direction, it allows flow, but from another direction, it does not. Yeah, I mean, this is what the casing shoe does. But the casing shoe technology, let's say, or the idea from Carl Baker, is just this hydrodynamic shape. It allows fluid to, it helps fluid go from inside to the annulus. That was the idea. That was his, I guess, the patent that he wrote that made him so successful. And his name is still alive. It also helps centralize the casing and minimizes hitting on rock ledges. It's basically easy to move the casing string down, okay? It's shaped like a rocket, It's able to move through the narrow pathways easily. I think you understand that. And it also makes it hard to get stuck. So imagine if I was running a casing shoe in a casing that the end of it was like this. It looks like this. Or, sorry, let me make it like this. Do you think it would have been, don't you think that it would have been stuck somewhere very easily compared to this? That's why it's the casing shoe so easy, so helpful, so practical. This is another picture of a casing shoe, again, upside down. These are basically the equipment, the different parts. That's one design of a casing shoe. There is so many designs. The outer portions are made of steel and generally match the size of the casing and threads. The inside, including the tabber, which is basically the float valve, is made of cement or thermoplastic. Since the material must be drilled out, thermoplastic is something that basically it will disintegrate by application of heat. When you drill, temperature goes up. It helps if you use something that will help you break it. Any questions on this stuff? Pretty simple, pretty simple. Now, the cement classes, just like with casing, you have cement, different kinds of cement. Some are used for different processes. In oil field in America, we use what we call Portland cement, which is a pretty, Portland, an island off the coast of England. That was basically the name from, is basically the chemical name is hydrated, whatever, silicate, something. It's composed of 4 oxide, calcium, silicon, aluminum, and iron oxides. And it's used, there are several classes, and the classes of cement are indicated with a letter, okay? The most common ones that you see in the oil field, doesn't mean that it's the only ones that you see in the oil field, is A, which is ordinary, most vanilla kind of cement. B, moderate to high sulfate resistance. C, high early strength requirements. G, basic, no additions other than calcium, sulfate, or water. And H, very similar to G. Now, it doesn't mean that there is no D, there is no E, there is no F, there is no I. I know there is some letters that are basically not, but we don't really use them as common as those. Those are the ones that we use most commonly. Now, this is the base, okay? The class is the base of the cement blend that we are gonna use. But there are several additives that we can add to our cement blend to change some properties based on what we want. And this is why those experienced cementing people, if you tell them, they will discuss with the operator and they will understand what would be the challenges on cementing this well, and they will add the appropriate additives into their blend so that it gets the parameters that you want. And there are several types of additives. We have here, let me just, for the people online, I will want to be able to use my mouse. Accelerators, what, it doesn't let me write. Anyway, it doesn't let me write that high. What are accelerators used for? They reduce what we call WOC, which is weight on cement. So if you want the cement to solidify fast for whatever reason, you will use an accelerator. Some of them are calcium chloride, sodium chloride, basically a salt, gypsum, sodium silicate, dispersant, even seawater. And the benefit is accelerated setting, basically. Retarder is the opposite, okay? It increases thickening time, takes longer, and it also reduces the slurry viscosity. Now, if you reduce the slurry viscosity, you get added benefit. It can flow easier through narrow pathways and stuff like that. Typical kind is lignosulfate, which is used in the mud for to reduce viscosity in the mud as well. Organic acid, CMAGC, we did that in the first class. And you basically increase the pumping time and allows easier flow. Weight reducing additives make it lighter, okay? Bentonite is a good example. Acapulcite, it basically thins out the cement, okay? It makes it thinner, makes it less dense. Diatomaceous earth, these are light stuff. Microspheres, foams, different stuff. You get lower density. Heavyweight additives, if you want to increase the weight, like hematite, this is iron oxide. It's heavy, right? It's very heavy. lignite, barite, which is using the mud to increase the mud weight, sand, dispersants, etc., etc. Additives for controlling low circulation. Now, low circulation is a big problem. They have tried everything in the mud, everything. When I say everything, even walnut covers, walnut shells, sorry. Now, same thing for cement. They have also tried everything. But the best thing really is, look at that walnut hulls. They have it here. They have even tried that. Cellophane flakes. But the best one, I don't think it's here, but I will tell you, is basically bentonite. Bentonite, because it builds like a filter cake around the hole. Bentonite is what you have, sorry, Rock. What you have, oh yeah, bentonite diesel oil, so it is here. It helps build the mud cake around the well, a thick filter that prevents fluid from escaping. That's what it's used for. Because low circulation means that your cement is escaping through the formation. Okay, you want to prevent that. You use bentonite, it creates a thin layer on those walls. And yeah, it works with the mud and the cement as well. Filtration control additives for squeeze cementing, for long liners, blah, 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 blah. Polymers, dispersants, latex, CMHEC. Now on dispersants, again, it's basically, it thins out the cement. It allows you to pump it easier, at a lower pressure. It makes it easier to pump. You need less horsepower. You have, again, salts, lignosulfates, which basically, it thins out the mud, you know? Different polymers. And then you also have other additives. This is a lot of additives. We can have a whole class on cementing, okay? But we are not. Because this is an advanced drilling class. Part of it is cement. You know, in some places where they don't teach petroleum engineering and they teach drilling, like a whole degree is drilling. You basically take these classes on cement and you learn about cement. But what you learn about cement is basically what you are going to learn if you go for training for a company on cement. And it's going to change after a few years when new stuff are coming up, because as we speak, people in service companies are working in advancing these. They come up with new additives every day. They test them, etc., etc. What we try to focus on is the fundamentals. So you can learn all the details when you go for work and they're going to train you. But here is what you need to, okay, this is the additive that I want to use it. This is the reason why I want the additive. And these are some uses and some examples. You don't need to memorize this stuff. But these are, from PetroWiki, the most important additives from the Lake 2006 is basically the Petroleum Engineering Handbook, the second volume, which is on drilling and completions. And some of you may get a job in this stuff, so you will know about this. Yeah, as we speak, service companies are working like crazy for finding new additives, testing them. Sometimes they work, sometimes they don't work. Okay, so I think now it's about the time that we see the first equations in this class.
I want to ask a question.
Yeah,
I don't think you mentioned it. The setting time of cement.
Yeah.
How do you plan around it so that your cement does not set
In the wrong time.
Before actually reaching the?
Well, you know how much time you will need, how long you want it to set. And the cementing guy who's very experienced is gonna use the appropriate additive blend so that it doesn't set too early or too late. He will use either retarder or accelerators, right? If he wants it to thin fast to solidify early, he's gonna use accelerators. If he wants it to solidify late, he's gonna use, yeah. And he's gonna make a little bit of a sample in a cup in his cabin and test it there.
At what time release?
Yeah.
But on the feed, can't maybe something happen and it's
Okay.
set before?
No, if something happens and you cannot pass through, you will pump some retarders to delay it. And then you are gonna pump some dispersants to make it thinner so that you can pump it through. If not, it's unlikely that you get there. Well, it's not unlikely, but you will accept defeat and then go for remedial. It means that we had an issue with the cement job. But these people are so experienced that,
Yeah.
I used to hang out with a guy from Halliburton that was doing cementing. He was like very comfortable working alone, and he was like, he would hang out in my cabin and he would come over in the morning and get coffee or something. They know what they are doing. They know what they are doing, and go ahead.
Yeah, so like what he's saying, the cement setting, you see that whether you want to delay it or you want to accelerate it. So the delay, as I said, the retardant, if you want it to delay, but if you want to speed it up, you use the accelerator, this additive that you add. So the gypsum is one of the common things that if you want to delay the retardant, then you have the, I think, the calcium chloride for the accelerator to accelerate the cement slurry as an additive to accelerate it. So it depends on what you're working and the time you want. So you mix it according to that.
So basically, a lot of it has to do with some of the chemicals that you add. They take water from the cement slab. They rob it away from water. So it's like you are removing water from it. You are adding something that likes more water, and it takes the water away from them. But how do those additives work, etc., is a different kind of science that is basically, you don't care how it works as long as it does the job that you want it for, but you want to use the right thing. So you want to talk to the cementing guy and explain to him, and he would be the one who will suggest, because he understands like how, and obviously it's not gonna be, they haven't drilled just one well in the region. They have drilled a lot of wells in the region. They know what they did in different wells, etc., etc. It's not like they are serious people. They know, and they have to. They stand out to make sure they see cement coming out of the well when they are basically pumping down. They are sometimes they stand out in the cold, waiting to see cement flowing out of the well, which means that it has circulated through. In the cold, it's a it's a tough job. But yeah, they come over and do the job. They are contractors, basically. You know, Halliburton fired his own son because he was late at a job one time.
Wow.
Yeah, my advanced drilling professor was there. He's that old. It was like he told us that they showed up to go and do the job, and they were counting each other, and basically were missing one person, and they figured out it was Halliburton's son who was missing, and they were like, let's not tell them who is missing, but the time was going by, and he wasn't showing up, and they had to say, and then a few minutes later, Earl Halliburton was on the radio firing his own son.
Wow.
Yeah. I wonder what year did this happen, but Like our advanced reading professor he was 85 10 years ago when I was taking these classes, you know?
Wow.
Yeah.
Not alive again.
No, he's still
alive.
As far as I know, I saw him a few days before COVID. He came over to Louisiana from Texas to give us the research seminar. And he said, "Hi, how are you? Are you doing good? Yeah, blah, blah, blah." And then that was it. I haven't seen him since.
Wow.
Anyway, subsurface pressures. Any questions before I move on to this important topic of how you calculate subsurface pressures? Okay. It's gonna be important stuff, but it's not, and of course, we're not gonna start throwing equations at you without okay. In the petroleum industry, mostly upstream, we use API gravity, depends in degrees API. That is used to quantify liquid densities. And this is very different from specific gravity, which is used widely in engineering. Okay, API gravity is for petroleum engineering. You know what API stands for? Yeah. Okay. So API gravity is not the same as a specific gravity, but it's very, very is related. Okay. We have this equation for the API gravity. Okay, so we have API gravity is 141.5 divided by gamma minus 131.5. Do you know what gamma is? Specific gravity, what it is? Specific gravity?
Or what?
No, what is specific gravity?
For gas, it should be the ratio of the density of gas to the density of air. If it is for
Okay.
water, density of liquid.
This is for liquid.
If it's liquid, it will be density of the liquid to the density of water.
Okay, great. Great. So what is the unit of gamma?
Dimensionless.
Okay. What is the units of API gravity?
Also dimension.
Uh-uh.
No, degree is degree.
Yeah,
Is degree, yeah.
yeah, that's correct. That's correct. So fresh water, what would be its API gravity?
10.
10, not 1.
Not one, yeah.
Okay. What if I have a heavy fluid? Like Canadian heavy or California heavy. What would be its API? Will it be bigger or smaller than 10? What do you expect? What API gravity you want to see? You are
It'll be smaller.
to be smaller. What gamma you are gonna see? Very big. So big gamma, small degrees API, right? The other way. Okay, don't get confused with that. What if it's a light oil? Like very light.
Very high API, low specific gravity.
Yeah. So for reference, West Texas Intermediate is roughly 39.6, 40 API gravity. Yeah, sometimes gas-specific gravities are given as a ratio of density to air. So be careful when you're using gamma. Is it gamma for gas? Is it gamma for liquid? This equation here is for liquids. Okay? Because the gamma would be different for gas versus liquid. This is only for liquid. Now the hydrostatic weight. Now, when we say hydrostatic, the term hydrostatic is very, very abused. It has two meanings, and it's used at the same time. It's used both, I guess, in the industry. It comes from the word hydro, which is basically in ancient Greek, it means water in ancient Greek. In our world, hydrostatic weight, it basically means the weight of a fluid, okay? It can be any fluid, any fluid. If I know its density, I can tell how much pressure it exerts underneath it, right? very easy. That would be the hydrostatic weight. But if I say I assume the weight of this fluid is hydrostatic, or I assume hydrostatic weight, you really mean that assume that this fluid weighs the same as fresh water. So it has two meanings. And every time you see the word hydrostatic, you need to be asking yourself, what is it used for? Because it's very confusing. It's ridiculous that they are using these terms interchangeably. But if I say, for instance, pore pressure in this reservoir is hydrostatic, it means that take the depth of this reservoir, multiply it by the density of fresh water, and this is about roughly its pressure. But if I say the hydrostatic weight of this fluid in the well, it means that I need to take the density of this fluid, multiply by the depth, and it can be whatever, you know, it's just the hydrostatic weight of the column, you know. So it's used very much interchangeably. I talk about it in my other class too, 575. It's a little bit confusing. So every time you see this word hydrostatic, ask yourself, what does it mean? So for gases, it's a little bit more challenging to find the hydrostatic weight. Sometimes we can assume it's weightless. So that makes it easy. So it doesn't weigh anything. Sometimes we use a complicated expression which is based on empirical correlation. And the empirical correlation, they have this thing that they are simple. They are basically equations with weird numbers with a lot of decimals. It's basically curve fitting between data, but they are not always effective. It's easy to apply, but they are not always effective because you get the correlations from somebody who did experiments at certain conditions and derive some correlations from curve fitting. He fit curves through his data and gave you the equations of those curves. And that's what you are using. But it's not necessarily always applicable. It's simple and not always effective, you know? Some other times there is a rule of thumb that you can use that if you go from point 1 to point 2, you can assume that the change in pressure P1 to P2 would be given by this. Now, don't use this equation unless I gave it to you to use it, okay? It's a ratio. And then you go delta, the change in true vertical depth, as we call it, from in feet times 25 divided by a million plus 1 times P1 would be equal to P2. Yeah, this is a rule of thumb. It's like, it's there to make your life easier, but don't apply it unless I tell you it's applicable, because gas from gas can vary, okay? It can be very, 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 very different. So this one is true vertical depth. And we're going to talk about it later on. What does that mean? By the way, I think we might be ready to give the homework maybe after this class, actually, but I'm not sure. I can maybe give it early, and then, but I think by Thursday, you'll be able to do the homework. So I can have it due next week. Anyway, so Bokun asked me a couple of days ago, how do you do the casing seat selection, right? I thought you wait, you're gonna see this is what you wait. So when we drill a well, we have to have the mud weight, the mud density to stay between within a certain window, okay? You want it to stay above the value of pore pressure, which is indicated by the blue line here. This line basically, and you want it to stay below the fracture pressure, which is indicated by this line here. Okay, you want your mud weight to be here. If the mat weight is here, it means that you are drilling through rock that has pore pressure that is higher than your mat. That means you are gonna have fluids from the rock coming into your well. This is called a kick, and it's very bad. You don't want that. If you do that and you don't deal with it properly, you're gonna get a blowout. If you are drilling with a very high mat weight, you're gonna fracture the rock. Okay, you are gonna fracture the rock, and then you are gonna lose mud through the rock. When you lose mud through the rock, you are gonna remove mud from inside your well. The pressure will go down, and basically it's gonna be as if you are here, and you are gonna get a kick for different reasons now, because you lost your mud. That's when you have lost circulation. Okay, now pore pressure and fracture pressure, they are terms that are very, very loose, especially the second one, the fracture pressure. Because as you see, when we did in geomechanics, fracture pressure can be 2, 3 different values, and you need to choose the smaller one, right? And same thing with with pore pressure. Sometimes you have breakout pressure, which is a little bit higher than that, and it can still cause damage. So basically, for every line, you have a bunch of different pressures, and you choose for the red line, you choose the smallest one. For the blue line, you use the largest one of this list, let's say. Okay, but bottom line is that you need to be between those two lines. And this is called the mud window, okay? Mud window. You need to be here. Your mud needs to be here, okay? It cannot go above or below for reasons that we discussed. Draw a plot with the pressure equivalent density or equivalent density on the horizontal axis and the reverse depth on the vertical axis. This is what we did here. Now, when I say equivalent density, we're gonna see why. And you're gonna see in the first homework. Density and depth can be combined to give you pressure, right? To give you the pressure below the mud column. The undergrads know who took the class with me, but I will show you the equation that you do that. But every time, and I want you to be very comfortable, if I give you pressure and depth, you can give me density equivalent. If I can give you, I give you 2, you give me the third. I give you pressure and yeah, so pressure and depth, you give me density. I give you density and depth, you give me pressure. You see, you need to be very comfortable working with those. I give you 2, you give me the third, basically. Draw lines of the formation, pore pressure and fracture pressure. This is what we have here for the mud window. And then draw a pathway using vertical and horizontal lines within the mud window to determine the length of each casing string. This is how you do the casing seat selection. You can do it in one of 2 ways, bottom-up manner or top-down manner, okay? Both of them work. They're gonna give you slightly different results, and you need to then make a smart decision, thinking of economics, thinking of other stuff, which way you'll go. Now, any question on the mud window? Where it says here, and I know there is a typo, it's not my plot, equivalent mud density, think of it as pressure, okay? Pressure increases, depth increases, okay? And these are the 2 lines. And I want to use this diagram to see how many casing strings I need to use for my well, okay? So this is, well, this is the bottom-up casing design, okay? I start from the bottom left, where there is A at the bottom. There is I gave myself a safety margin from each line. I went a little bit to the right for the minimum bound, and I went the lower bound of the mud weight, and I went a little bit to the left for the upper bound. So I start from the bottom left here, okay, A, and I go up until I hit the upper line, and then I turn to the left. 1 second. Oops. No. Okay, I stopped sharing accidentally. I go here, and then I go to the left, and then I hit point C, and then I go up again, and then I go to the left, I hit E, and then up again. So I go up and to the left, right? I start from the bottom left, and I go up, left, up, left, up, left. Okay, how many casing strings do I need now? Huh? Three. That's correct. I need one up to 1800. I need another one to 45, and I need another one to 12,000. So how much of a total of a casing string do I need? Like 12 and 45 and 18, add it up, you get the value. Right? Okay. Any questions in that method? Bottom up?
The line is just a vertical line until you meet
Yeah,
it
yeah.
first.
Yeah.
So the safety margin, what determines the safety margin that you use?
You can use 0.5 as an arbitrarily set.
Okay.
Company policy, you the engineer. This is basically how confident you want to be. You want to go like more, the more you go, the bigger the safety margin you use, the more casing strings you will have to use later in your design, because your mat window narrows down. You want it as wide as possible, but you also don't want to go on either side, then you have problems, right? Rocky, are you okay?
Yeah. So if you give your safety margin, let's say from the pore pressure safety margin to be, you go more than, let's say 0.5 or other things, and then for the fracture pressure, you also give a higher safety margin. Based on economically in terms of designing for the casing, which one is most appropriate in terms of economic benefits?
Well, you want the mat window to be wider.
Why? But because maybe you are afraid, maybe if you are very close to whether the pore pressure, the safety margin is small, and for the pore pressure and the safety margin for the fracture pressure is small. Maybe you might mistakenly get close to, then go and then hit the pore pressure where you can get a kick.
Yeah, but if you want to be risky with the safety margin, you're gonna get less casing string, less steel that you will need to put in the weld. Because if you add it up, it's gonna be like something like, imagine if I didn't have any safety margin, okay? Or if I had something small, let's draw it. How will it look like? I will start from here, and I will go here, and then I will go here, and then I will go here. I will need two, right?
Okay.
I saved myself. How much? You can add it up and see how much I saved myself.
Yeah, two.
Okay.
Two of the casing.
Well, I saved here. I do 12,000 plus 4,500 plus almost 2,000. I don't know what is the total. And now I go to what? 12,000 and 3,000. I go only 15,000 feet of casing versus what was it? 12 plus 45, that's 16 and a half, plus 18, or let's say 2.
That's 18,300.
18,000.
300.
So I saved myself 3,000 feet of casing but I got rid of my safety margin. Let's just say I don't get rid of my safety margin. I use half of the safety margin. I'm more risky, but I'm still supposedly safe if I did it right. And we're never confident on our mud window, right? So, yes, I'm saving myself some money, but it would be worse if I blow up the well, right? So, this is one way of doing it. It's not always the better one. The other one is the top-down method, which is it's the opposite. I start from the top right, and I go down, then to the right, then down again, then to the right. I go like this, then I turn right, I go down again, turn right, and then down again. Okay? This also works. This method also works. I go down and to the right, downwards and to the right. Okay, and now what do I have? I have 12,000 feet, 6,000 feet, and 3,000 feet. This is like 21,000 in total. Okay? Before I had 18,000 something. Now I have more. It just happens that this method gave me more casing that I will need. Doesn't mean that this is what I will do necessarily. Both methods work if you do them right, you know? Both methods can work. And then you need to make a decision. Safety and economics will play a role. Now let's assume that I don't have any safety margin. Okay? I don't have any safety margin. This is what I will start from here. This is my A. I go down. This is my B. This would be my C. This would be my D. So the end basically. So I only need two, right? Again, I will need one 12,000 and one 5,000. So I have 17. But again, I got rid of my safety margin. I'm just playing it theoretically speaking to show you that the wider the window, the better the casing design. Now, every casing string I run down is not just the money of the steel. It's not that much. I mean, it's a lot, but it's not that crazy. I also need to go in with a bit. It's going to make my hole smaller, right? And smaller, and smaller, and smaller. That's why that well in Gulf of Mexico, the Blackbeard had 14 casing strings in it. If I could do it with 7, if I could do it with 10 safely, I would make the company a lot of money, right? That's why I told you, wait, when you ask me how you do the casing design, how do you decide? Because we're gonna go through this. Now, how many casing strings? Like I said before, depends on the mud window. The thing is that we call it mud window, and generally we say it's between fracture pressure and pore pressure, but it's not really the same. Sometimes it's not pore pressure, it's like the breakout pressure, because the breakout pressure is higher than the pore pressure. So that becomes the limiting factor. Breakout is when your hole starts collapsing. We talk about it in geomechanics. And sometimes there is a low circulation pressure, which is lower than the fracture pressure, and then that becomes the limiting factor on the other side of the mud window. But generally, you have this mud window. Basically, it's the window that your mud should stay within in terms of density, and you make your design accordingly. It limits change during tripping, running hole, or tripping out of the hole. And many times, well, almost always, what I did in the previous 2 slides, it was idealistic. It was assuming that the mud weight is static. But when the mud moves, you need to take that into account. It makes things much more complicated. We're going to see how, especially on the second module. When you select the casing, what is gonna go through that, you cannot put, if the inner diameter of a casing, say it's 5 inches, it doesn't mean that the casing you are gonna run into it would be 5 inches outer diameter. It will never go through. It needs to have some sort of clearance. And in the oil field, we have this sort of rule of thumb that the clearance should be between 0.13 and 0.18, the ratio, basically using the outer diameter of what you are gonna put inside, the casing string that you are gonna run inside. So basically, if I have a borehole size of, sorry, let's just say, a casing that is 5 inches outer diameter, I should be able to pass it through a 6 1/8 inch of inner diameter inner diameter of a hole or a casing, other casing. Ideally 6.5. Okay, and so on and so forth. And these are roughly the sizes that are available. Liners in general are these sizes here. But basically, this is what we use. This is not a mandatory, it's a rule of thumb. It's practical. You use this ratio C as a clearance, which is inner diameter of the outer casing, the inside of the outer casing, and the outer diameter of the inner casing. So let me just draw it. You have this is the casing, inner and outer, and then you have, use another color, orange, yellow. Oh, yellow is not gonna be visible. Let me use blue. The inside of the tubular. So you care about, let's see. You care about this. This is the IT, inner diameter of the outer tubular. And this is the outer diameter of the inner tubular, right?
I don't get what you drill your hole,
Yeah.
right? Then your hole is so then you want to do your casing. Then definitely your casing is supposed to be what? Smaller than your hole. But there is supposed to be some clearance.
Yeah.
Where is that it should be between 0.13 or 0.18. Or we can use this but now you are talking about the casing, the inner casing, the outer of the casing.
How do you calculate this clearance?
For this one?
No, the clearance ratio, C, is basically the outer diameter, the inner diameter of the outer casing, which is this, minus the outer diameter of the inner casing, which is that, or tubular, divided by 2. This is what this is.
Yeah. So can you draw it like a vertical, like in a normal scenario?
Yeah, sure.
Yeah.
So it's like this. I will try. This is the inner tubular. And then the outer is this. And I want you to know, to tell me, to calculate C, you need to give me this, which will be this. And then you are gonna give me this, which will be this. Right?
Okay.
You get it? All good? Okay. Yeah, this is how you do it. This is a practical recommendation. You don't have to do it, but yeah. And I think actually we are ready to give the first homework. I will, because we're gonna do the YouTube model. Okay, and then we're gonna do that. Okay, so we should be ready. Let me see the homework again. I might post it, but by the end of class on Thursday, we'll be able to do it. Okay, so during the weekend, you're gonna have a nice weekend doing the homework, which is easy, and you need to do a good grade on the first one, so you start the class nicely with a good grade. It's very easy. Easy but important. Okay, I will see you on Thursday. I did upload the recording of lecture 7 or 6. Last Thursday, I forgot to send the announcement, but yeah. Anyway, thank you very much. Have a nice rest of your day. I have office hours today, 1 to 4, if you have any questions. And yeah, I'm available. The TA is available. Yeah, thank you. Thank you, Donald.
Thank you.
See you. Oh, thank you, Tito. I didn't see you on the call.